Okay, today I'm pleased to introduce today's session, Advanced Retrieval Augmented Generation Applications with Llama Index, and our guest speaker is Laurie Voss. Laurie is VP of Developer Relations at Llama Index. He's been a web developer for 27 years. He was a co-founder of NPM Inc., and he cares passionately about making technology accessible to everyone by demystifying complex technology topics. Welcome, Laurie.
Hi, thanks for having me. Shall I go ahead and share my screen?
Yes, please.
Excellent. Thank you, Christy, for the kind introduction. Hello, everyone. So what are we going to be talking about today? We are going to recap retrieval augmented generation very briefly. What is it? Why do we do it? What are the challenges of retrieval augmented generation? How do we do it? And then we're going to go into Llama Index and how it helps you get retrieval augmented generation done. We're going to dive into 7 techniques that can level up your RAG game, and then we'll wrap up by talking about how to get your app into production. Let's start with retrieval augmented generation, or RAG. Fundamentally, RAG is a response to a limitation of LLMs. They are trained on enormous mountains of data, but they are not trained on your data. Your data sits behind your firewall where OpenAI can't see it. It's sitting on hard drives or in databases or behind an API. Your data is the most interesting data from your perspective. And if you want an LLM to process and answer questions about that data, you have to give it to them. But you can't simply give them all of your data at once at the moment, simply because they can't handle it. If you give ChatGPT all of the documents at your company at once, it will barf. Context windows are in the hundreds of thousands of tokens at the moment. But your company probably has hundreds of millions of tokens worth of data. Even in a universe where an LLM had an infinite context window, it would still not be practical every time you want to ask a question to give an LLM every piece of information your company has ever had. You have to be selective, and that is where the retrieval part of RAG comes in. You have to give them the most relevant context, and that is a very complex problem. But there's more to it than just context size. There are a lot of unique challenges to how you do RAG. What do we get out of doing RAG? We get 4 things. First, we get accuracy. Obviously, we want the right answer, but by retrieving the most relevant data and giving it to the LLM at query time, we make sure that the answer is not just correct, but as complete as it can possibly be. Incomplete answers can be just as misleading as answers that are entirely wrong. Closely related to accuracy is what we call faithfulness. Terms differ for this across the industry, but essentially it means that there are no hallucinations. LLMs try too hard to be helpful sometimes. Giving them the data and only the real data helps prevent them from inventing things. Nobody wants hallucinations. They're one of the most frustrating parts of building AI applications. Another big challenge is recency. While you can, to some degree, improve accuracy and faithfulness by fine-tuning a foundational model on your data, doing so is very time-consuming and expensive, and your data changes all the time. Sometimes it changes from minute to minute. So the only practical way to keep up with data that changes in real time is to use retrieval augmented generation. And finally, there's provenance, by which we mean the LLM can say where it got the answer. Being able to cite your sources is good in an academic context, but when you're talking about search, it's often essential. Finding the document that the answer came from is often the point of a search. It's not just a nice to have feature. So that is why we do RAG. Now let's get to how we do RAG. The core of RAG is retrieval, and there's a bunch of ways that you can do that at the highest level. You can, for instance, just do keyword search using the same algorithms that search engines like Google use and have been using for years. They are pretty good at finding information, it turns out. We've been working on that problem for a long time. And then there's structured queries. If you have a huge relational database full of data, it doesn't make sense to dump it all to text and then give that to an LLM because you have all of this valuable relational context. Instead, LLMs are getting pretty good at writing SQL queries, and you can get the LLM to query your database and retrieve important context that way. And then there's vector search, which is the one that you hear about most often, partly because it's the new kid on the block, but also because it's really uniquely powerful. For vector search, the first thing you do is convert your data into numbers, specifically gigantic arrays of numbers called vectors. The models that do this work are closely related to LLMs, and they encode your data as meanings rather than as keywords. The total set of available vectors is enormous, and that is known as the vector space. So for that reason, converting text into numbers is therefore known as embedding your text into vector space, and therefore the numbers are called embeddings for short, which is confusing, I think. There's a couple degrees of separation between what it is and the name for it, but embeddings is what we call them. The effect of embedding all of your data this way is that you can then take your query and embed it into vector space the same way. Because of the way vectors encode meaning, the answer to your query is likely to end up mathematically nearby in vector space and can be located with relatively simple math. So this allows you to do retrieval augmented generation. You embed all of your data, then you embed your query, you retrieve context that's nearby to your query, and then you feed that context and your query to an LLM, and you get a reasonable answer to your query. It's not just regurgitating the context, it contextualizes and explains it as well. So you can use this amazing vector search, or you can use keyword search or structured queries, but of course you can do even better and use all three of those at the same time. Keyword search is going to work really well if what you're looking for happens to be the right keyword. And vector search will work even if you use a different keyword that has the same meaning as what you're searching for. So in practice, you want to do all of them to some degree. So that brings us to Llama Index. Llama Index is an open source framework that connects your data to LLMs. We're available in Python and TypeScript. And connect your data to LLMs is one of those problems that's easy to say, but very tricky to do in practice. Let's take a look at a typical RAG pipeline. First, you load your data from your sources. You ingest it and you prepare it to be processed. There's a lot of complexity in that process. Then comes indexing. This is where you embed your data, preparing it for vector search, which, like I said, is not the only way, but a great way. And then you put that data in a vector store. There's lots of choices to be made about how to put it into a vector store and obviously which vector store to use. When you're ready to query that data, you first have to retrieve the most relevant context. This is another task with a ton of hidden complexity, often involved in post-processing of the data that you have retrieved. Then you have to combine that context with a prompt, and everybody knows that prompting is its own whole art. But combining a prompt with context can also be a task with hidden complexities. And finally, you get your result, which depending on what you're doing might require further processing, like turning it into valid JSON or something like that. So there's a lot going on here. RAG is magical technology, but magic is tricky to get right. So let's talk about how Llama Index gets involved at every stage of this process. Before you get started, you have to pick your LLM. We support dozens of LLM models and more every day via APIs like Ollama and hosted options like BentoML. Let's start with ingestion. The very simplest form of ingestion is to just load a bunch of files on disk into memory directly. And here's how you do that in 2 lines of code. In Llama Index, you can do the actual ingestion part in 1 line of code. The second line is your indexing. This simple directory reader that I'm showing here can handle a huge variety of file formats, including CSVs, PDFs, Word files, and also images, audio, and video for when you want to do multimodal things. But what if your data isn't in static files? Like I said, your data lives everywhere. What if it's in Google Drive or Notion or a database of some kind? Llama Index also provides a registry called Llama Hub, available at llamahub.ai, and the hub provides a huge library of software to help make building your RAG applications easier. That includes connectors to connect to your favorite data sources, tools for building agents, data sets for evaluating your applications, and a set of things we call Llama packs, which are essentially arbitrary code packages, which turn various complicated tasks into one-liners. I'll mention all of these again as they become relevant, but the one that's relevant right now is the loaders. So if you need to load from some other source, you can check out Llama Hub, but for this example, we're going to stick with Simple Directory Reader. If you're happy with our defaults, then you're done, and you can move on to line 2, which is where we index the data and send it to an embedding model. But you might not be satisfied with our defaults, in which case you want to build an ingestion pipeline. This lets you configure a series of transformations. You can specify how you want to split up your documents for embedding, and you can specify what metadata you want and what embedding model to use. The result is a set of nodes that you can see on line 11, which you can then use to start indexing on line 14. And of course, in production, you'll probably end up running the same pipeline over and over as you experiment with these parameters. So we allow you to cache your ingestion pipeline and reload it instantly if nothing has changed, only rerunning the parts that have been modified. That brings us to the second stage, which is indexing. As I mentioned, this is the stage where you take your chunks of data and you embed them into vector space. We support a huge set of embedding models, just like we support a huge set of everything. These all have different performance in terms of both speed and quality of retrieval. Your workhorse here is the vector store index, which takes care of getting all of that embedding done, whether it's via a remote API or a local model. You'll see us call out to vector store index over and over in these examples coming up. Depending on your use case, you also may want to check out our knowledge graph index, which can take unstructured text and split it into entities and relationships that then perform entity-based queries on your data. But now you have all your embeddings, and it's time to move to the third step, which is to store them. We support dozens of vector stores. Vector stores are all doing roughly the same thing. They take giant piles of numbers and allow you to search against them using vector math. However, there is a lot of differentiation in the space, as we're going to see later, in which ones allow metadata filtering and hybrid search. I'm going to explain what metadata filtering and hybrid search are. Which brings us to the next stage, which is querying, and the thing that we're not going to be talking about very much, which is prompting. Other RAG frameworks talk a lot about prompts and prompt engineering, but we take a different view. LlamaIndex is a batteries included framework, which means that we have come up with excellent prompts already. They are tried and tested and they're finely tuned, and we've built them into the framework so you don't have to figure it all out yourself. Of course, if you want to, you can modify the prompts. That starts with the most basic thing, which is you can inspect the prompts so you can see what the defaults are that we've provided to you. And you can pass in your own, either in advance or at query time. The syntax of prompt customization will be very familiar to you if you've used any other library to do this stuff before. But essentially, prompting is giving arbitrary text to an LLM that instructs it on how to answer the question. So now we're at querying. Let's start with the most basic form of querying. We just get our index to give us a query engine, and we accept all the defaults this way, and we just run the query. This is great. This is part of why LlamaIndex is so easy to get started with, because you can go end to end from loading through ingestion to embedding to storing to querying and to your result in just 5 lines of code if you really want to do that. But of course, like everything in LlamaIndex, your query engine can be customized. What we're doing by default is retrieving the top 2 most relevant pieces of context of your data and returning them to the LLM for querying. But you can configure your own retriever as shown here. Here I'm setting similarity top K to 5, which means that it will select the 5 most relevant pieces of context as my context. You can also configure the synthesizer, that is how the engine puts the query together before it sends it to the LLM. There's a bunch of available strategies here that we don't have time to go through in this talk, but effectively what they all do is group your chunks of context together and query the LLM with them. Finally, you can create your query engine by combining your retriever and your synthesizer and querying the LLM. So that was exactly the same thing that we did in 2 lines of code in 10 lines of code so that we could show all of the stages involved in basic querying. I said that we would look at more advanced strategies. So let's look at the first of those. Excuse me. Let's look at the first of those, which we conveniently package up for you as the sub-question query engine. The problem that the sub-question query engine solves here is complicated questions. If you have a lot of unrelated data sources, it may require getting data from more than one of them in order to answer a single question. And that's impossible to do in a single query from a single source. So what this engine does is break your query up into a series of simpler questions using the LLM. Then, given an array of data sources, it routes each query to each data source appropriately and combines the answer from each data source into a single answer. In this toy example, we're creating just one data source. We've created a simple query engine, such as we had on previous slides, and we're assigning metadata to it, which specifies what the tool should be called and roughly what it does. The LLM uses this description to decide which data source is going to be able to answer which kind of question. You can have as many of these sources as you want. The next problem that we want to tackle is precision. Basic RAG can struggle with making sure the context is precisely related to the query. One tactic for handling that is known as small to big retrieval. In small to big retrieval, we break a large document up into single sentences and perform retrieval on those very specific sentences for maximum precision. But then at the synthesis stage, before we hand the query and the context back to the LLM, we go back and retrieve 5 sentences worth of context before and after the sentence we just retrieved. That's hence small to big. This gives the LLM more context to work with while maintaining the precision that we want. Getting this done in Llama Index is disarmingly simple because, again, we've done all of the work and packaged it up nicely for you. When creating our query engine, we can supply a list of node post-processors, which work after retrieval but before synthesis, and use the catchily named metadata replacement node post-processor with a target metadata key of window to automatically search through nodes, which all have links to their previous and next nodes, and link together the previous and next nodes before sending the query to the LLM. Small to big is precision by post-processing nodes, but you can also get better precision by pre-processing. One way that you can help the LLM out is to use existing metadata that you have about your data and filter on that before retrieval. In addition to using embedding retrieval, some vector databases natively support attaching arbitrary metadata to each of your embeddings. An excellent example of this technique is if you were dealing with documents representing annual legal filings of a company. You could attach the year as metadata and pre-filter your data on that, as shown here with the exact match filter. One of the key lessons here is that if you have metadata about your data, you can help the LLM by giving it less stuff to work with. You can say, I know this answer is going to be in the documents from 2021, so I don't need to give it context of 2020 and 2019. I can just give it this particular year and get it to do its magic within the documents that I know are relevant. Using the vector index auto retriever, we can describe each of the metadata fields and get the LLM itself to decide how to apply the metadata queries, allowing you to continue to query in natural language without any manual refinement on your side. As you can see from this list, most of the vector databases we support also support metadata filtering. Only a handful don't, so that's good news for you. Our next example is hybrid search. Embedding-based vector retrieval is truly magical, but like I said, as an industry, we have poured decades of effort into building search engines, and at this point, they're really pretty good. So some of the most interesting vector databases are actually search engines executing in Pivot. They allow you to do not just top K retrieval, but also use existing search algorithms, one of the most prominent of which is called BM25. Once you've got a database that supports hybrid search, using it is extremely easy. You just pass vector store query mode equals hybrid, and then pass a value called alpha. It runs the same query against both vector and traditional search. Alpha determines the degree to which search relies on results from traditional search or vector similarity. 0 means that your results come entirely from traditional keyword search, and 1 means they come entirely from vector search. And you can tune this number to get the best results for you. As you can see, the list of vector databases that also support hybrid search is a lot shorter. Not on this list is Vespa, because we haven't built a specific integration for it yet, but it does support hybrid search and works well with Llama Index. The reason I mention it is because Vespa was invented by Yahoo, and as an ex-Yahoo myself, I will always have a soft spot for Vespa. Another use case for advanced retrieval is complex documents. Not every document is just a pile of text. They often contain complex tables. So let's consider how we can break down a complex document into a set of simpler queries. But first, I need to introduce you to our ability to query tables in the first place. We have a fantastic built-in called the Pandas query engine. You create a Pandas table in Python, such as by reading in a PDF or by reading in a CSV file, and using the LLM, it can generate correct Pandas calls that query those tables to get the right values. We can then provide the description of each table, either from ourselves, or we can get the LLM to look at the table and derive what's in the table, and create a series of what are called index nodes. These are just like regular nodes that you saw me pass to vector store index during ingestion caching earlier, but the retriever I'm about to introduce will know to treat them specially. Excuse me. The retriever I'm about to introduce will know to treat them specially. Each index node contains an index to a dictionary that we're creating here. The dictionary consists of instances of Pandas query engines and one for each table in the document. Now for completeness, we'll show parsing the rest of the document, from which you can assume we have already extracted the tables. We create a vector retriever that operates all of our nodes, both the regular nodes and the index nodes. And now we set up a query engine just like we did earlier. A retriever, a synthesizer combined into a query engine. But this time, instead of a regular retriever, we use the recursive retriever. The recursive retriever expects a list of retrievers to use, so we give it the vector retriever we just created. It also knows that if it retrieves an index node, it should look up the index it finds in that node in a dictionary of subquery engines and perform a query there. So we pass it a map of IDs to query engines that we created just now on that previous slide and create the query engine with that. So now a query to the top level engine will result in retrieving all of the relevant nodes. And if one of those nodes is a table, then it will perform a pandas operation on that table to retrieve the exact result from that table rather than just trying to read the table as if it were text. Then it will return the synthesized prompt to the LLM, which will return the full answer in context. A very common advanced retrieval use case is wanting to query a SQL database directly. There's no end of really great data in SQL databases, so the use case here is obvious. Let's break this down and show how it's done. Under the hood, Llama Index is using SQL Alchemy, which if you've ever done data work in Python, you'll already be familiar with. But here we can just connect to a database and initialize Llama Index's own SQL database class. The SQL database class is handled by the natural language SQL table query engine, again, one of those really catchy names, which is another built-in from Llama Index. What this does under the hood is pass the schema of the table as part of the query to the LLM and gets it to generate SQL. This is obviously tricky stuff, so it works best on GPT-4 and other advanced LLMs like Mistral Large. But if you know the name of your table in advance and you're sure the schema will fit into the prompt, this is an incredibly simple way to get it done. You can see how this would fit well into the recursive retriever that we were just looking at too, because you could make SQL tables just another node that you can query in your retriever. But what do you do if that stuff isn't true? What if your table schema doesn't fit in memory or you don't know which table to query in advance? In that case, you can create a SQL and table node mapping as we're doing here. You create an index of each of the tables that you turn that into a retriever, which you then pass to the SQL table retriever query engine, which is yet another amazing built-in. This will search the index for the most relevant table and then pass that to the natural language SQL table query engine and perform the query as it did before. So it doesn't matter how many tables you have in your database, you can get the LLM to select which table is going to be the most relevant one and run the query for you. How does it know which table to query? It uses the LLM and looks at table and column names. But if you want to be more helpful, you can manually describe the tables, as I'm showing here, to give it more context of which table is likely to be helpful. The final use case that we're going to cover today will also be the most complicated because it's not just a retrieval strategy, it's an example of an agent in Llama Index. Our favorite example of this in the wild is our demo application, secinsights.ai. SEC Insights AI was initially intended as a demonstration of Llama Index, but now is a fully open source demo application that you can adapt and customize. What it does is you give it financial filings documents from one or more companies, and it can compare, contrast, and summarize them to tell you what's in the filings. In the latest Y Combinator batch, there's a company where this is their whole business, but for us, it is just a demo. Our first step here is to create a query engine for each of our data sources. Here they are very similar sources, they're just in different directories, but they could be entirely different query engines using any of the strategies that we've already talked about today. So one of them could be a SQL query engine, one of them could be looking at a pandas table, one of them could be a sub-question query engine. You can compose these engines together. But now, because this is an agent, we define tools to give it that it can select from. As we did earlier in our SQL example, we give the tools metadata so the LLM can decide which tool is going to best be able to answer a question. Now we define our agent, which is, again, surprisingly simple. We give it a nice capable LLM like GPT-4, capable of tool use. And we give it the set of tools that we created. Now, the agent, when given a query, will enter a loop where it tries to select the best tool, run queries over that tool, and continue until it gets an answer. In this contrived example, our query is very simple and our tools are very simple, but remember, you could have made any of the above examples that we talked about into just one of the tools available to the agent. So you could have had one doing sub-question query engine, another doing text to SQL, a third performing hybrid search. You can get up to some really amazing things by composing your sources this way. So we've seen how to build some amazing stuff, which brings us to the final step, which is getting it into production. I hope we have some listeners to the Latent Space podcast here. It is an excellent podcast about the rise of AI engineers and the future of AI generally. And recently, the host, Sean, describes 2024 as the year of Llama Index in production. And we completely agree. One great way to get your AI creations out of a notebook and into production is Create Llama. It is a command line tool loosely based on Create React App. It's an application generator that creates a ready-to-ship RAG application with a working front-end interface and a backend in your choice of serverless, TypeScript, Node.js, or Python. So you just run this one command and you've got a working app that you can customize and ship. It has dozens of options and templates attached, and it's a really great way to accelerate your development and get into production quickly. Here's a short list of companies that already have Llama Index in production. It's shorter than we'd like because the truly giant companies that we know are using it are often a little hesitant to say so publicly, but rest assured there are household names with Llama Index in production today. As a brief example, take Gunderson Detmer. As a major law firm dealing with startups, they have an enormous body of internal data informing their current agreements and the state of the tech world. ChatGD is an internal tool that uses Llama Index that lets their lawyers quickly query that corpus for relevant information and answer client questions more quickly. So let's cover again what we learned today. We talked about what Llama Index is. It's an orchestration framework, but it's also a hub of tools and connectors. And finally, a set of tools for getting into production. We covered the stages of retrieval augmented generation: ingestion, indexing, storing, querying, and brief. And we talked about Llama Index support for pipelines and pipeline caching, how Index works, the set of vector stores available to you, and what features they support. We briefly covered prompting and how you can customize your prompts and how to create a query engine. Then we went into those 7 examples. We started with naive top K retrieval, then we went into the sub-question query engine for more complex questions. We talked about post-processing for precision with small to big. We talked about using metadata filtering to increase the precision of queries and how that filtering can be automated by further using the LLM. We covered hybrid search to combine the best of vector retrieval with the best of traditional search engines, and we talked about the recursive retriever for indexing really complicated documents. Then we briefly dipped into the world of text to SQL and multi-document agents and how all of those different techniques can be combined. I hope that this was a useful look into your start of your journey into AI. We are still really early and everybody is learning. So if this was a little overwhelming at points, don't sweat it. I also hope that it gave you a sense of all the amazing things that you can do with Llama Index, and I look forward to seeing the amazing things that you build. Thank you all for your time and your attention.
Oh, thank you very much, Lori. Hey, so kudos on being an open source software. I have a question. Is there a commercial version of Llama Index available?
Yes, we have, in addition to the open source Python and TypeScript versions, we have in beta a service called Llama Cloud, which allows you to create a managed ingestion service that does all of this stuff for you using a GUI and just a few clicks. It's still in beta, but if you go to our website, you can get into the beta by contacting us.
All right, so you heard it here. Hot take. Okay, so we have a few questions. I see a couple in the Q&A window. So Daniel asks, does Index's built-in prompts solve the problem of asking off-topic questions like when was the universe made, but the website is about dog food? So that means your documents would probably be about dog.
That's an excellent question. No, our prompts don't specifically address that. Our prompts assume that you're going to be asking relevant questions. However, there are pre-processing and post-processing strategies that you can use to deal with that.
Okay. And question from Girish. Hello, thanks. Would you be sharing the slides?
Yes, absolutely. If you follow me on Twitter, my username is Seldo, S-E-L-D-O, and I will be putting the slides there right after this talk.
Okay, someone who does not want to be named. One of the biggest issues I face is the speed of search. Users are used to incredibly fast keyword search, but hybrid even ends up being a bit slower. What's the most initial way to manage results and speed? FTS on search engines being the use case. Just the recommended bare bones.
That is an excellent question. There are not a lot of ways to get around the fact that LLMs are going to have higher latency than traditional keyword search. One of the features of LLMs, however, is that they are essentially very complicated autocomplete. So they begin to answer the question immediately. It just takes them a little while to answer the question. So one of the things that you can do is stream your results. Users are in practice a lot more forgiving, waiting for an answer if it starts coming immediately. This is what ChatGPT does. They will wait up to 15, 20, 30 seconds, which is like an unheard of amount of time for somebody to wait for an answer, if the answer has started coming and they can see that the answer is going to be relevant to them.
Okay. So Mike asks, once I have completed my RAG-based app, but it's not performing as well as I would like, what parts of the pipeline and tools do you recommend to improve the accuracy, latency, and cost?
Wow, that's another really great question. People are really listening to this webinar. So accuracy, latency, and cost are three very different questions. If cost is your primary concern, then you're probably going to want to slide down your expectations in terms of accuracy and latency. One of the ways that you can get your cost down is by using a local model instead of a hosted model. There are lots of very capable local models, especially if you fine tune them on your data. A local model can, depending how you set it up, also improve your latency, because local models tend to be a lot smaller and therefore their answers are a lot faster. Accuracy and latency. Latency is a tricky one. Like I said, streaming can sort of give you a smoke and mirrors response to latency. But there's no better fix for latency than just throwing a lot of hardware at the problem. Accuracy is the most complicated one. Accuracy is what you can get out of using a really subtle query strategy. So a really finely tuned prompt, a query engine that splits your data sources up into multiple independent data sources and queries them independently using an agent. Those things can really improve your accuracy. You can also improve your accuracy, latency, and cost by messing with the size of your retrieved context. So when you are splitting up your data initially, you have to turn it into chunks. So those chunks can be very large or they can be very small. The smaller they are, the faster your responses are going to be, but the less context you're going to get in them. So you have to make this trade-off between how much context you want and how fast you want to be able to retrieve it. So as you can tell from my answer, which is sort of all over the place, like accuracy, latency, and cost, those are a complicated trio of sliders that you have to move around and pick the best combination of them for your application. I hope that helps.
Okay, thanks, Lori. So another question in the Q&A window. Anonymous, thanks for this talk, Lori. Very informative question. What uses does Llama Index have for data cleanup? I want to not retrieve, but actually do the opposite, insert data using my LLM, and then build out my retrieval pipeline. Any tools for this?
Huh.
Insert. Okay.
That is an interesting use case. I'm not particularly familiar with that use case, so I can't say that I have any particular tools to answer that one, I'm afraid. In terms of data cleanup, though, if you go to Llama Hub, there are lots of preprocessors available that will help you when you are ingesting your data in the first place to clean it up. One of the best ones is a PII detector that will help you get rid of protected personal information if that's a concern for you. But the more general question here is, how do you get your data clean? It's not really an LLM thing. Getting your data clean is an old school data science ETL question. And so all of the previous decades worth of work on how to clean up ETL data are what apply. You have to do pre-processing, you have to do ingestion, you have to do pre-aggregation, and you have to do a lot of filtering. It's all a lot of nuts and bolts programming that doesn't really have much to do with LLMs, but is very important to getting the quality of your answers.
Thank you. PII tool sounds really useful. Okay, so Terry asks, can you elaborate on how RAGs will be useful in a world where LLMs that have larger and larger context windows? Also, could you share your opinions on using open source versus closed source LLMs?
Absolutely, both good questions. As I tried to mention at the beginning of the talk, we've all heard of Gemini 1.5 Pro, which is going to have a 1 million context window. We have got at Llama Index, obviously, a lot of questions about what does that mean for retrieval augmented generation. The answer is you still need a way to connect your data to this LLM. You're still going to need to know where it is. You're still going to need what is the most relevant data. Like I said, if you had a 1 million, even if you had like an infinite context window, you wouldn't want to, when you were answering a question, give it 1 million tokens worth of stuff. There's no need to like throw 1 million tokens worth of data to answer a very simple question if you know that you can get it in just 100 lines of context. So you're going to get, it doesn't matter how big the context window is. If you have an infinite context window and you could get the answer in 100 lines of context instead of 1 million lines of context, the 100 lines of context is always going to be faster, no matter how big that context window is. So we were talking about accuracy and latency and speed. Your latency is going to be better if you're managing to give it relevant context, and also your cost is going to be better if you're giving it relevant context instead of your entire corpus of data every time. As for open source versus closed source LLMs, well, I used to run NPM, so I'm a big fan of open source. I think open source LLMs are doing amazing work, and I think having access to the models democratized is a really, really excellent trend.
Great. Um, so I think I see a few other questions in the chat window. I see Rajesh was asking, does the RAG support querying on Microsoft Excel data?
Yes, it does. We have an adapter for querying Excel data.
And now we have another.
You'd,
Oh, sorry.
you'll find the answer on Llama Hub rather than in Simple Directory Reader, though.
Okay, great info. And back in the Q&A window, another question, Thierry, what kind of LLM projects would you recommend for AI engineers looking for a job in the field? You mean, I could think he's thinking like a portfolio project, maybe.
Yeah, that's an excellent question. The thing that's most hot right now is agents. Excuse me. Everybody wants to see agents that can demonstrate tool use and actually take actions rather than just answer questions. So if I were looking for like a fun LLM project that would also demonstrate that I know what I'm doing, I would combine RAG with an agent. So imagine an agent that can read your calendar and then set up new appointments. That's using RAG. It's going to have to look at your calendar. It's going to have to figure out, when you're busy and when you're free. And then it's going to have to take an action like creating a new event on your calendar. That kind of project demonstrates the full gamut of stuff that you can do with LLM applications. So something along those lines is a really good project. But thank you for that question.
Great, thank you. Okay, now I'm going to go back to the chat window. Is Tossin asks, is it possible to build a framework to load various kinds of data sets into vector database? Okay, any sample code or approach? Does he mean different? Yeah, okay. I mean, that's what it's all about, right?
Yeah, that's what Llama Index is for. Llama Hub has hundreds and hundreds of connectors for loading from all sorts of data sources. If you have lots of different data sources, you have some choices to make whether or not you want to combine them all into a single vector store or you want to maintain one vector store per type of data. Personally, I think storing them in separate data vector stores is a good idea because then you can use tool use, like I said, you can use sub-question query engine or something like that to say, okay, I got a question that is probably best answered by this data source versus a question that is best answered by this other data source. And you can keep them separate and answer questions separately.
Okay, so we will have the recording out in a few days. And then back in the Q&A window, Daniel asks, what's a use case where Llama Index might not be an appropriate solution?
Llama Index is very firmly focused on RAG and using agents to solve RAG. So if that's not what you're doing, you're going to find fewer tools for us to do that. So it's hard to, it's like, don't try and build Photoshop using Llama Index because that's not what we do. But if what you're doing is retrieval augmented generation, we're very firmly focused on that use case.
All right. And then I'm going to go back to the chat window now. Stefan asks, what library is the generated Python server based on? Flask, Fast API.
The generated, I assume you mean the API that is generated by Create Llama, and that is a Flask API. That's a Flask application.
Okay, I'm going to jump back to the Q&A window. Anonymous asks, I hear more and more about using PG vector store, but what data type would you actually put in the PG to use it? Maybe I read that wrong. What kind of data type would you actually put in the PG to use it as a vector store? Oh, he's talking about PostgreSQL, but they've got PG vectors. Time series vector, wait, TS vector seems basic. I'm not sure. TS vector.
I'm not sure either.
Okay.
Maybe rephrase that question and try again.
Yeah. Anonymous, can you please rephrase your question and we'll try to answer it. Thanks. Okay, I think he's trying to type it. Nope. Okay, I'm gonna dismiss that one. Okay, are there any plans to support code similarity search? Code completion.
Yes, or rather, we already do. You can use, there are models that are very good at code search, and we connect to those LLMs. So you can all, and those embedding models that are really good at code embedding. So you can do that today.
Awesome. And Rajesh asks, we are working on building Gen AI platform for enterprises. Is it possible to partner with Llama Index?
Absolutely. Please go to the contact us form on our website and we will happily partner with you.
All right. So yeah, I think that looks like we got a wrap on that. Any last words of advice? I think people, at least myself, I'd like to know where we can find out more. Where can I get started? Will we get some links for that?
Yeah, they'll be in my slides, but also if you just go to docs.llamaindex.ai, that is a great place to get started.
Okay. Okay, one more question coming in, Q&A window. Anonymous. Okay, he's rewritten his question. To use Postgres as a vector store that can be retrieved by Llama Index, would you just embed your existing text data using the embedding model and store that as a vector data type?
Yes, that is absolutely what you would do.
Okay, perfect. All right, I think we've answered everyone's questions. And you gave us a lot of information. It's amazing how much Llama Index does with the in-memory vector store part. So thank you, Lori. I learned a lot too.
Thanks, Christy.
All right, thanks. See you next time. See you next time, RAG folks. Bye.
Bye, everybody.